Assalamualaikum warahmatullahi taala wabarakatuh. Okay, in this session, I want to continue to analyze beam using stiffness method. Okay, I want to revise back what we have learned previously. Okay, so let's say we have this beam, just a simple beam to this is a continuous beam. Okay, like this and this. Okay, so this is a continuous beam. This is node number 1, node number 2, node number 3. Okay, this beam has loaded with a uniformly distributed load of 50 kilonewton per meter, and there is a vertical load of magnitude 350 kilonewton. Okay, the length of this is 5 meter, this is 2 meter and 2 meter. Okay, so there are two elements, element number 1 and element number 2. Okay, so I want to focus on the analysis of equivalent element nodal forces in order to establish equivalent nodal forces. I just want to focus on Q naught. Okay, so to solve this, as usual, the procedure to solve this. Okay, step number 1, as usual, we need to establish K1 and K2 and then K. Okay, K1 and K2 is element stiffness matrices for element 1 and element 2, and after that K1 plus K2 is equal to structure stiffness matrix. Okay, since there are 1, 2, 3 nodes, there are 3 nodes, so there are 6 total degree of freedom. Okay, for K1 and K2, I don't want to discuss in detail the answer for K1 and K2, but I want to highlight on the degree of freedom. Okay, degree of freedom only. Okay, by looking at this, there are, okay, here, okay, this is the constraint system. This is also constraint. This is also constraint. Okay, only one unconstrained. Okay, so for the label, this is number 1. Okay, number 1 here, 2, 3, 4, 5 and 6. Okay, so the most important thing is to label the element stiffness method correctly. Okay, so using the label, the degree of freedom label that we get from the main diagram, we should label near YZ, far YZ. So near YZ for element 1 is 2, 3, 4, 1. 2, 3, 4, 1. Okay, and for element number 2, the label is 4, 1, 5, 6. 4, 1, 5, 6. 4, 1, 5, 6. Okay, this label is important, yeah. This label is important because in order to establish equivalent element nodal forces, we will use the same label. We label from near to far. Okay, so from this we will calculate all the values in the stiffness matrix. In the element stiffness matrices, we calculate using formula. We calculate using formula, and we will complete all this with value, and after that we will establish the structure stiffness matrix. Okay, in order to solve for the unknown displacement that is located at node number 2, we have to use this equation. Q is equal to KD plus Q naught. Okay, what I want to highlight here is Q naught. Okay, Q naught. Okay, now what is Q naught? Q naught is equivalent nodal forces. Q naught is equivalent nodal forces, and equivalent nodal forces is actually to understand what is actually equivalent nodal forces. Please remember, this is about member, means that loading, there are loads on member, okay, not about nodes. Okay, nodal forces is a load on load that is subjected directly at nodes. However, for Q naught, it is about member with loading, okay, member with loading. It can be UDL, it can be point load, it can be triangular load, okay, but all these loads subjected on the member, okay, on the member. If load subjected directly at node, such as moment subjected at node 1, moment subjected at node 2, then it is Q. Okay, so basically for equivalent nodal forces like this, it will focus on the UDL like this. Okay, this UDL is subjected on the member. This is UDL, right? This UDL is subjected directly on the member, and point load that is subjected on member 2, on member element number 2, or member 2, on the member, at anywhere on the member, not at join. If this 350 subjected at node 3, then it will be the nodal force, not Q naught. Q naught is equivalent nodal force. So the simple tips to identify the difference between Q and Q naught is about member. Okay, I want to focus on this. Okay, what is Q naught? Q naught is equivalent nodal forces, and Q naught is come from equivalent element nodal force. Means that there will be Q1 naught for element 1 and Q2 naught for element 2, and this 2 is called as equivalent element nodal forces. Means that we have to determine all this first. Okay, what is Q1 naught? Q1 naught is like this, 4 values. Okay, because it will depend on labeling for K. It is the same. Okay, 4 values, because here at each node there are 2 degrees of freedom. Each node has 2 degrees of freedom. Okay, so one element has 4 degrees of freedom, so there will be 4 Q. Okay, 4 Q means that vertical force moment at both nodes. Okay, so Q1 naught like this, Q2 naught like this. Okay, so the label we just have to follow whatever degree of freedom label in element stiffness matrices. It is for element 1, it is 2, 3, 4, 1. So we just have to label the same. 2, 3, 4, 1. Here is 2, 3, 4, 1. And for element number 2, it is 4, 1, 5, 6. 4, 1, 5, 6. Okay, like this. So how to establish this? How to determine all this value? What we need to do is we have to refer to the appendix to see the formula. Okay, like this. This is for UDL. It's 50 kilonewton per meter and 5 meter. Okay, so for the vertical reaction, it is 50 times 5 divided by 2. It is WL over 2. It is 125. And for the moment, fixed end moment, for the fixed end moment, it is WL squared over 12. W is 50, L squared times 5 times 5 divided by 12. It is 104.167. 104.167. Okay, this is the fixed end moment. Okay. Okay, for element number 2, for the degree of freedom, okay, the label is 2, 3, 4, 1. So we need to fill in the value. Okay, fill in the value. Okay, for position number 2, it is equal to 125. For position number 3, it is equivalent to 104.167. For position number 4, it is 125. And position number 1, it is negative because it is in opposite direction. It is negative 104.167. Okay, we will do the same for element number 2. For element number 2, it is point load 350, 2 meter, 2 meter. Okay, so P over 2 is 350 divided by 2, it is 175. And for the fixed end moment, it is PL over 8. PL, P times L is 4 over 8. It is 175. Okay, for the degree of freedom, element number, this is element number 2. The previous one is element number 1. Okay. So the label for degree of freedom is 4156. 4156. So we need to compare. So for position number 4, it is okay. All values has the same. Okay, 175. So it is 175. So it is 175, 175, 175. And for 6, it is opposite. So it is negative 175. Okay, so to establish the equivalent nodal forces, it is Q naught equal to Q1 naught plus Q2 naught. Okay, so Q naught, since this is for the beam, okay, this is 1.56, just like structures in the matrix. Okay, 1, 2, 3, 4, 5, 6 position, we get the value from this. Okay, for position 1, we have negative 104.167 plus 175, so we get 70.833. We get 70.833. Okay, position number 2, it is 125. Position number 3 is 104.167. Okay, position number 4. Number 4 is 125 plus 175. It is 300. Position number 5 is 175. and position number 6 is negative 175. Okay, so this is how we establish the equivalent element nodal forces and equivalent nodal forces. Okay, we have to do this for all beam elements whenever beam has loaded with UDL or point load on the member. Okay, on the member. Basically, for beam and frame, Q naught is compulsory to calculate. So I suggest you to follow this step in order to have this value, because this is the simplest way to establish the value. Okay, I repeat again. So if this is the question, this being consists of three nodes, and one okay, there is one unknown rotation or one unknown, okay, 1 degree of freedom in unconstrained system. The remaining the reaction at the support, there are 5 unknown reaction. Okay, 5 unknown reaction by not considering the axial force in the system. Okay, so as usual, step number 1, we have to establish the element stiffness matrices and structure stiffness matrix. I don't want to show this step here because okay, I have shown to you previously in the few previous examples. Okay, what most important I want to highlight is the position of the degree of freedom in the element stiffness matrices. Remember, we have to label the degree of freedom according to near to far end condition, near to far. Since for beam there are 2 degree of freedom in y and z direction, so we have to label as near yz, far yz. So for K1 it will be 2341, and for element number 2 is 4156. Okay, why this is important? Because we will label the same for the element for the equivalent element nodal forces. Okay, I straight to jump to Q naught and Q1 naught, Q2 naught like this. Okay, for capital Q naught, it is for equivalent nodal forces, means for the beam, for the structure. And we also have a small letter of Q labeled as Q1 naught, Q2 naught. So small q is to represent the element. Okay, naught is to represent the equivalent nodal forces. Okay, because there are 2 elements, so it is called as equivalent element nodal forces. There are 2 elements, so Q1 naught, Q2 naught. So Q1 naught, Q2 naught like this. Okay, there will be 4 values depend on the degree of freedom for each element, and the label for the degree of freedom will be the same with elements stiffness matrices. Okay, for element number 1, Q1 naught, it is 2341, and for element number 2 is 4156. Okay, how to establish all this value, how to determine all this value inside the equivalent element nodal forces. Okay, it is like this. This is for element number 1. Element number 1 is consists of UDL. Okay, UDL 50 kN per meter subjected along 5 meter length of element number 1. So we will calculate the vertical reaction and fixed end moment for element number 1 as this. Okay, so as you can see in the screen, so we compare with the degree of freedom. So where is the position of 2341? It is like this. Okay, it is like this, the position. So what we need to do here, after we label all this, we just have to compare. So for element number 2, for position number 2, okay, number 2, 3, 4, 1, right? So for number 2, position 2, it is equivalent to 125. Okay, 3, position 3, it is equivalent to 104.167. Okay, for position number 4, it is 125. Same, we compare the same position. Okay, and one is in opposite direction, so it is negative 104.167. Okay, we will do the same for element number 2. Element number 2 consists of a vertical load that is subjected on the member at the middle, at the center. So we calculate the vertical reaction as well as the fixed end moment using the formula given in appendix page 3. Okay, so okay, and the other one is the degree of freedom for element number 2. It is 4 for y, 1 for z, for the near node, and for the far end node it is 5 6. Okay, so we need to transfer the value into the Q2 node. Okay, let's look at position number 4. Where is the value for position number 4? 4 is 175. Okay, 1 also 175, 5 175, and position number 6, the direction is opposite, so it is negative 175 here. Okay, so after we get all these Q1 node and Q2 node, we have to combine in order to establish the equivalent nodal forces. So what we need to do is like this: Q node is equal to Q1 node plus Q2 node. Okay, Q node must have 6 value from 1 to 6, depend on the total degree of freedom in the system. So just like the structure stiffness matrix, the value must be written in order, means from 1 to 6. So we have to find all this value, okay, based on the value we get from Q1 and Q2 node, okay, from 1 to 6. So find all this value from this. Okay, find all the value from this based on the position for 1, 2, 3 until 6. So we get like this. Okay, so to solve for the unknown displacement, as usual, remember this is Q is equal to KD plus Q naught. So we will get Q. From this, Q1 is for moment. There is no moment, so Q1 is 0. Okay, there are 5 unknown reaction: Q2, Q3, Q4, Q5, Q6. Okay, this is okay. We bring Q0 here because we want to solve for the unknown displacement. Okay, 70.833, 125, 104.167, 300, 175, and negative 175. So this is equal to K times D. So there is only one unknown reaction. The rest is all 0. The rest is all 0. 1, 2, 3, 4, 5, 2, 3, 4, 5, 6. Okay, so from this we will get the unknown displacement because the boundary is here. This is the boundary. Then we will get, okay, the equation like this. The equation is like this. Let's say if this is x, so this is x d1 is equal to 0 minus 70 is derivative 70.833. So d1 is equal to negative 70.833 divided by x. Okay, so this is how we analyze beam using stiffness method. Thank you very much. Assalamualaikum.